This video is going to cover solubility, just the basics of it. We'll do net ionics in the next video. So solubility is the last piece of the perfect chemical equation, and it looks at whether or not a compound can dissolve. So to be soluble literally means that a compound dissociates or dissolves. It comes apart. And anytime it does this, we put the little symbol of an AQ behind it in an equation. To dissociate, aka it breaks into ions, into pieces, and that AQ stands for aqueous, because for these initial equations we're going to be dissolving everything in water, in fact. So for example, we all know that table salt is soluble. It does dissolve. If you take a big spoonful and stir it around in water, it goes away and now you have salt water. But what actually happens is that my compound becomes two separate ions. A smidgen more specific than that, if you remember the concept of polarity, our polar water molecule, that negative side is going to want to hang out with the positive end of, or the positive piece, of my sodium chloride. So that is literally going to pull that piece and take it off somewhere else. To the bonds of friendship, they have been broken. Similarly, over here with the Cl, the positive end of my water is going to want to hang out with that negative end. So my water molecules are literally pulling apart my ionic bonds. So this is what it means for something to dissociate, to break apart, to be soluble. There are two more terms that you need to be familiar with. The first one is to be slightly soluble, and this means that only a teeny tiny itsy bitsy bit dissolves. But as far as most beginning chemistries are concerned, this is also known as not soluble, insoluble. There's not enough that dissolves to matter. To be insoluble, as I just said, is to be completely not soluble. It does not break into ions. It does not dissociate. It stays as a solid, represented by this little S. This is, in fact, a product. If you think back to your evidence of a chemical reaction occurring, I can't speak today. So for a reaction, RXN still stands for reaction, to occur, we must make something new. So in the case of this insoluble substance, we have created a solid where there was not one before. But how do you decide whether or not a substance is solid? Is it just arbitrary, or is there in fact some kind of plan? Well, this is chemistry, so of course there is a plan. There are these solubility rules, a series of rules that help you decide whether or not a substance is soluble. Rule 1 says that all common compounds of group 1 and ammonium, NH4, are soluble. This means that any compound containing a group 1 ion, so sodium, potassium, lithium, hydrogen, rubidium, cesium, francium, you won't really see these last two too much. Oop, you can't even see that. Or the NH4 ion, if you see those, it's soluble, good to go. So, ammonium chloride, we already said it is soluble. It breaks into ions when put in water. Manganese 4 chloride. This is also aqueous. It will dissolve. Now be careful when you break this into ions, because all of our ions separate, which means these 4 chlorides are in fact 4 chlorides. We could do some other, I don't want to use that one. Some other ion. So again here, this is soluble. Breaks into, my goodness, I'm making all kinds of mistakes. It's ions. The only ion to be careful of is fluoride. Fluorine is kind of iffy. It does not like to dissolve at all. I specifically avoid this ion in my class because even sodium fluoride is kind of iffy. It doesn't dissolve terribly well. It will if you stir long enough, but it's kind of iffy. So that was rule 1. Rule 2, maybe I should write these. I don't know how well you can read that other paper, is that all nitrates, acetates, and chlorates are soluble. So the same deal applies. Anytime you see any of these ions, that substance is soluble. Once one piece is soluble, the whole compound is soluble. So, for example, lead 4 nitrate, even though there's a lead in there, that nitrate makes this soluble. So be on the lookout for those 3 or your group 1 ions. Our third rule says that all binary compounds of a metal and a halogen are soluble except when that metal is silver, mercury, or lead. Excuse me, I did those out of order. Oop, there goes my flower. So, this is actually where that fluorine comes into play. That F, even though F is in fact a halogen, it's kind of iffy. It doesn't always like to dissolve. But binary compounds, so anything made of 2 things, composed of a metal, so anything to the left of the zigzaggy line on the periodic table, and a halogen, so this would be group 17, chlorine, fluorine, iodide, bromine, any of those guys. This is soluble unless that metal happens to be silver, mercury, or lead. So, silver chloride, one of my exceptions. This stays solid. It is insoluble. You do not break it into ions. Something like iron bromide. This is a metal. This is a halogen. We're good to go. So it will, in fact, break into its ions. Rule 4. Get a new piece of paper here. Rule 4 says that all sulfates are soluble except, and this one has several exceptions, barium, calcium, strontium, lead, silver, and mercury, specifically mercury 1. These last 3 are slightly soluble, but again, that means that just a tiny, tiny bit will in fact dissolve. So, again, something like calcium sulfate, it's one of my exceptions. This one stays solid. Manganese 4 sulfate. Manganese is not one of my exceptions. Thus, this one will in fact break apart. My 5th rule says, except for rule 1. So rule 1 said that anything from group 1 or ammonia is solid, or is soluble, excuse me. So, that being said, carbonates, hydroxides, oxides, silicates, there's several ways you can write silicates, and phosphate are insoluble. They are not soluble. So, iron 2 carbonate, not soluble. Sodium carbonate. Sodium is a group 1 metal. There's that rule 1 exception. So this guy is soluble. He will break into his respective ions. The last rule is a little bit weird, and this is the rule for sulfides. Sulfides are insoluble except for calcium, barium, strontium, magnesium, sodium, hydrogen, and ammonium. So this one's kind of weird because it's a little backwards. So calcium sulfide is in fact soluble. This is the only exception I think that goes the other way. Anything else? Iron sulfide. Iron is not one of my exceptions, so this one stays solid. So anytime you run into a compound, you identify its solubility just based on these rules. Tick through each one in particular until you find the one that pertains to that particular compound. In the next video, we will go into net ionic equations, where we use this idea of solubility to predict whether or not a chemical reaction has actually occurred.